They're welcome to talk to each other. These problems. Let's tell each other jokes or something. Make this class more fun than it already is. Got questions? Raise your hand. Let me know.
Sorry. That's the trend.
No way.
Alright,
Yeah. What do you call a cow jump?
say it's the same destruction. What do you call it? Switch those two. The numbers. Which one? Diagonalized. Once you have a diagonal, don't you just Isn't that what this is doing now?
Four right uses two.
Just gonna call it X and come.
That's gonna be the transpose. Yeah. So
you can multiply it back. Order it. Associate different ways.
that's what it is.
This is my question.
And I define the eigenvalue
My first step.
and I was wanting to like
I just
It is.
Yeah, that's what that's what he said. I'm curious, like if you look just dropping
yeah, like I was like, you could do that. I saw the first ones had that. It's just the first two. I realized that 10
the last one.
all the rest of these are proofs, aren't they? I went,
Minus one.
I could not like the questions or anything. I was like, I don't know if I'm from the online one is fine. But apparently I just sucked at it last time.
My
Combination. So these span a point.
round
So actually any vector that starts at zero.
more complicated. You have your main bracket.
That's also like the last one. That's what
Brackets. And the main bracket winner out of all of them.
you can find.
Round gets like a certain amount of money.
So
And then the top overall gets a certain amount of money. It's a little bit. And then by the end,
Been a whole vector on your meal prepping.
the main bracket
And I
gets
woke up this morning and realized I
and
like
then the
every day.
winner overall
Overnight.
scaled.
No, I don't have lunch for the week. How many people are there? Like, is this just?
is
And I don't have time to make more. That was the whole point of meal prepping.
So you win a lot of money. Molly may or may not do that.
She did that. Okay, so in
You're bound to win.
just a minute, I'm going to move to some work that shows the work for number one that a student did. Okay, so if you want to take a picture of this, you want me to, before we get off.
It isn't. I got 20 or 21 turned in. Couldn't stop. I just couldn't stop. So just consuming me. Isn't it the oh, it doesn't say aren't they? Just roll it. No. Because I accidentally.
Here's one student's work. Yours might look a little bit different, and that might be okay. We'll talk about this. So you can compare yours to the one up here.
When we do all the tests,
Yep, we just write it out.
Yeah, so the problem, looking at what they did, I did something similar. I
actually have to do it.
get steps with I eventually found out.
I got to
When in doubt, self-evident once you find the
because I got so
this is what I got from
yeah, for my top.
right.
Just find the eigenvectors.
What I got for S. Is that what you got?
I got the same thing. I just wanted a different way. I saw the B this fast.
Oh, yeah. Oh, yeah.
So you find the it's one over determined.
Easy to forget.
So let's dive into this. Okay, feel free to stop me or ask questions whenever we go through this. We didn't have questions right off the bat. All right, so we're trying to rewrite B as SAS inverse, where S we create S by finding the eigenvectors of B. A is a diagonal matrix, and it has the eigenvalues of B here. And then S inverse, the inverse of that. So to start off, we need to find out what those eigenvalues are. So we subtract off lambda on the diagonal, and then we take the determinant. So you get 3 minus lambda times 3 minus lambda, and then minus a negative 1, so minus this ends up being minus 1 equals 0. So this part's the characteristic polynomial. This is the characteristic equation, and multiply it out, combine like terms, factor it down, you get 2 and 4. Okay. After you do this a bit, you can sometimes figure out what your eigenvalues are before. At least some of them without even doing all of that. So for example, you might start subtracting off numbers down on the diagonal until you can get like this column to equal this column or this column to equal a negative of this column. You're just trying to get two linearly dependent columns, right? So you might start subtracting off 1, I have 2 and negative 1, negative 1, 2, no, subtract off 2, then I get 1 and negative 1, negative 1, 1. Oh, those are linearly independent. If one is a negative multiple of the other one, one's a negative of the other one. If you subtract off 3, I get 0 and negative 1, negative 1, 0. Those are independent. If you subtract off 4, I get a negative 1, negative 1, negative 1, negative 1. Oh, there's another one. Because those are linearly dependent columns. So sometimes you get lucky just by looking, or it's simple enough that you can pick out some values. Even if you can't find them all that way, sometimes it helps if you can find one. It can help when it comes to factoring down the characteristic polynomial. Okay, so we found our eigenvalues, and so now we find our eigenvectors. So we subtract 2 off the diagonal, we get the 1, minus 1, minus 1, 1. Augment it with 0, solve. You add the first row to the second row. You get a row of zeros here. It's got a free variable. X2 is a free variable, so you can let it equal 1 or t. Since if we're finding a whole solution set, we taught you to write this down as x2 equals t, and x1 equals x2, so x2 would equal t. So then you could write it as t equals 1 times 1. But this student just picked x2 equals 1 to get one vector there. Okay, so 1, 1 is an eigenvector for lambda equals 2. And we can check that. You just go back and multiply 1, 1 times this matrix, and you'll get 2, 2. So you can just do that in your head. I hope. Then for lambda equals 4, subtract 4 off the diagonal and augment with 0. You get a bunch of negative 1s here. Subtract the first row from the second row, you get a row of zeros. You multiply the first one by 1, and then you get 1, 1 by a negative 1. Change the sign there. So x2 is a free variable. You get x1 equals a negative x2. So you get the vector 1 and a negative 1, 1. You may have done it differently, where you may have ended up with 1, a negative 1. That's just fine. Okay? Any scalar multiple of this is still an eigenvector. So we can multiply by a negative 1 and get 1, a negative 1. Okay? That's what I had when I did it, but you don't have to have negative 1, 1. You could have 1 and 1. You have 2 and negative 2. Something like that. Okay, any questions about finding eigenvalues, finding eigenvectors? Okay, been doing this for a few weeks now, so hopefully you're comfortable with that, especially with 2 by 2s. So now we can write S as the eigenvectors. Does it matter which order I write the eigenvectors in? It doesn't matter. I can pick these in whatever order. I just then have to match up the eigenvalues. Or if you pick your eigenvalues here, then it does matter. You've got to match up the order of your eigenvectors with the eigenvalue. Okay. So here, since we put 1, 1 first, 2 is the eigenvalue. It corresponds to the eigenvector 1, 1. So I need to put that 2 in the first diagonal position. And then a negative 1, 1. That corresponds to the eigenvalue 4. So the 4 goes in the second diagonal position. So you mean the 4 is in the second column because the eigenvalue associated with 4 is in the eigenvector associated with 4 is in the second column. So if you could switch these two and you switch and the 4 go here and the 2 go there, that's just fine. And then you can calculate S inverse. Luckily, this one isn't too bad. We can use that 2 by 2 shortcut. This work down here just shows, yeah, you could put the negative 1, 1 first and the 1, 1 here. Your diagonal matrix would just look good. It'd still be. Okay, questions? Okay. So we're going to work up to the second one where we're actually calculating the thing to the 10th power. But what we're going to do now is work up to why this makes sense. Like really what we're doing when we do this. Okay. So so suppose I want to compute what I gave it to you in the second part. 3 and negative 1, negative 1, 3 to the 10th power times 1, 3. That would take a long time to do that all out by hand. It doesn't take long to throw it into Wolfram Alpha. True. It doesn't do the computation this way, though. It does what we're doing. So it can save itself some time. However, if we can think of this matrix as just a scaling transformation, then it can be much easier. Because this is the matrix of a scaling transformation where I just have values along the diagonal, and that to the 10th power is just the diagonal values to the 10th power. You can start just multiplying this matrix times itself to convince yourself that that's true. You get a squared, b squared on the diagonal, and you multiply again, you get a cubed b squared. Okay. This is very easy to take to the 10th power. That's not so easy. So, but the trick is we need to be able to think about it as a scaling transformation. I might be able to think of this as a scaling transformation. I forgot to put that in this slide. If I can find the eigenvectors, because some transformations, a lot of transformations, they're just scaling in a couple directions. I put might here because we might, the eigenvectors might not be real. We're not working with that situation at any time in this class. But also if the geometric multiplicity for the eigenvalues is not the same as the algebraic multiplicity, it's not diagonalizing. Okay, that was one of the big theorems like that this section built up to when you're reading, was when is a square matrix diagonalizable? Well, those algebraic multiplicity, the algebraic multiplicity has to equal the geometric multiplicity. Okay. So that's why I said I might. So we'll have to check that. So if this does scale, it's going to scale along eigenvectors. So let's find the eigenvectors. Well, first I have to find the eigenvalues. We already did that. So this means these are the eigenvalues. That means that this matrix, it just doubles in one direction and quadruples in another direction. That's a lot easier to think about than this transformation here, in thinking of it in the standard coordinates. But we have to define what directions those are. What direction does it double? What direction does it quadruple? Well, those are the eigenvectors. Well, we found already the eigenvector. So 1, 1, we know it doubles. As I mentioned before, you multiply it, you'll get 2 by this matrix, you get 2, 2. And then you multiply by 1 and -1, what are you going to get? 4 and a -4. Better be. It's an eigenvector associated with lambda equals 4. So you just get 4 times that. You don't even have to multiply. So yeah, we did that. So the trick is we're going to move from this complex thing, and we're going to try to think about it as a scaling transformation with a simple diagonal matrix. The hard part is we have to change bases. We're not going to think about it in the standard coordinates. We have to think about it in this eigenbasis. Okay, so these are the coordinates we're going to think of. All right. Man. Dang it. I didn't send you the updated.
Send me the update. I wasn't able to get it on my email, so I had to go through it this week.
I accidentally skipped a slide. I deleted a slide. So I fixed it after the last class, and then the Corey curse struck. Okay, so to think about the transformation that this matrix does as a scaling transformation, I need to think about it in the eigenvector coordinates. So the vector we care about is 1, 3, but that's in standard coordinates. So I'm thinking about this point here. I go over 1, up 3. That's in standard coordinates. Okay, we're really comfortable doing that. Okay, but for this to think about this as a scaling transformation, I have to do something else. So what is this vector in eigenvector coordinates, or our eigenbase coordinates? So I've already given it to you over there, but think for a second, look over there. Can you see the 2 and a -1 coordinates in the graph? So here we've got the vector 1, 1. Here we've got the vector 1 and -1. How many 1, 1s do I need to get to there? 2. How many 1 -1s do I need? A -1 of those. Go in the opposite direction. So this point I can think about as 1, 3. I can also think about it as 2 and -1. They're just in different coordinates, different units. Okay. But this is going to be a lot easier for us to use because eigenvectors just get scaled when I multiply. So I can do a very easy multiplication now. So instead of doing this times that, which I know isn't that hard, okay? It's the same as this times this. But the values I get out won't be the same, but they will represent the exact same coordinates, the exact same vector. The first one will be in the standard basis. The second one is in the eigenbasis. So now, what are the coordinates of Q in the two bases? Okay. So actually, what do I get out? Why do I care about Q? What if I do this multiplication? What do I get out? 3 times 1, -1 times 3 adds to 0. -1 times 1, which is a -1. 3 times 3 is 9. 3 minus 1 is 8. So when I do this multiplication, I get the vector 0, 8. What's the coordinates of Q in the eigenbasis? So think about that for a second and talk to your neighbor. How would you represent that on the graph? Okay, so what you were thinking? You don't have to take that path, particular path, but in the end, you do have to take 4 that way and -4 that way. You could snake this way if you wanted to, or you could go this way and then that way. Doesn't matter the order. You're going to end up in the same spot.
What if Q was on the point 0, 7? We would have to do half values then?
Yep.
for
Yeah,
eigen?
it'll be a half. So 3.5. Yeah, 3.5, maybe, and 4.
3.5,
Or 3.5, something like that. Yeah. Okay, good question. And that's what you get when you do this multiplication. 2 times 2 is 4. I get 0 in the other place, and then do this out, I get 0 times 2 times, and then the -1 times 4, I get 4 and -4. They represent the exact same point, but one of these multiplications is easier than the other. Okay, especially if I'm going to do it 10 times. But I just have to think about it. The coordinates in different coordinate systems. Okay. So yeah, any other questions? Yes.
How did you find the -1 vector?
Good. So that was, how did I find the 2, -1 vectors? 2 ways. I emphasize just this geometric way over here. So it took 2 of these vectors, 2 1-1s, and a -1 -1. So these are my 2 basis vectors. This is the vector 1-1. This is 1 and -1. Those are my 2 basis vectors for the eigenbasis. You may have had a -1-1, which is fine. So it's had something different here. So this was easy enough. I could see, oh, if I take 2 of those and a -1 of these, then I see that P is the coordinate for this in this coordinate system is 2 and -1. But algebraically, the way we do it, like, what's the meaning? Like, we're trying to find how much of 1-1 and how much of 1 and -1 do I need to add together to get 1-3. That's back to the peanut butter bread example. How much of peanut butter, how much of bread do I need to get certain protein and fat? And we can represent that as a matrix system. Here's AX equals B. And what's the easy way to solve this? We'll multiply both sides on the left by the inverse. So another way to get that 2, -1 is to multiply by the inverse of this. And we'll get to -1. Yes.
Yeah, this is back to the power thing we were talking about, but I remember we learned another way to find the power of a matrix using just the eigenvalues. What's the advantage of the diagonalization way to find it?
It's the same thing. It's just structured differently.
Okay.
So
So did that trick that we did only work with diagonalizable?
yep.
Okay.
Yeah. Yep. Yeah, like you're talking about like the book does it before you get to diagonalization, trying to say, hey, if you think about tries to show you the power of thing in the eigenbasis, then the math looks out nice. Yeah, we're just structuring that. The math is the same, we're just structuring it differently. So it's all in it's all just a simple matrix multiplication. Good question. Okay. All right, so I'm going to go back and recap now what we've done. And we're going to build up to that diagonalization formula. So I wanted to do this. Oh, sorry, I'm not quite up to my recap yet. Sorry, looking ahead. So we wanted to do this, but now it's easy because I can think about this multiplying by 3, -1, and -1, 3. I can think about it as just multiplying by 2, 0, 0, 4. But instead of multiplying by the 1, 3 vector, I'm multiplying by 2 and -1 because I'm changing coordinates and I'm thinking in the eigenspace. And so I can take this to the 10th power, very easy, then multiply that by 2 and a -1, boom. But our answer is not in standard coordinates. Our answer now is still in the eigenbasis. So this tells me, oh, this first number tells me how many 1, 1s I have. And this number tells me how many 1, -1s I have. But I would like to know in the end, nice to have it in standard coordinates. And so I can just do this math. Multiply this times the 1, 1 plus that times 1, -1. And we can rewrite that as, this is, of course, we can rewrite that as a matrix multiplication. So this is 1, 1, 1 and -1 times this vector, and I get this. Okay. Yes.
I understand that the 2, -1, that came from looking at the graph. We did have a graph where it was like a 4 complex. How did we get that?
Great question. So we get it by multiplying by the inverse of this matrix. Because we want to know what A and B, how much of this first vector and how much of the second vector do I need to get to 1, 3? And that is this system. I'm solving for this system. And an easy way to do that is to multiply both sides on the left by the inverse of this matrix. Okay. So, good question. Okay, so we went through the whole process. Eventually we got this, which is what you would get if you actually multiply this by itself 10 times and then multiply both. Okay. But we did it in a roundabout way, but in a roundabout way that saved us a lot of calculations. Maybe not quicker, because it was very slow going through all this. All right, so now we're going to put things together. So what do? We converted 1, 3 from the standard coordinates to the eigen-based coordinates by this. So this, right back to your question. So to get 1, 3, to get the coordinates in the new system, we took our first vector and multiplied it by the inverse of the matrix we created with our eigen.
So is it necessary to convert that vector into the coordinates instead of just like writing out a inverse P multiplied by the vector in the coordinates?
No. So like we're building up to this, right?
Yeah.
And you're like, no, you multiply these all together if you want.
So which way?
So the reason I'm emphasizing this is because this gives you the reasoning on what we're doing, what that S inverse is doing, like the way to think about that. So when it comes to calculating, you can do whichever way you want. So good question. All right, so we started with 1, 3. Like we really had a matrix times 1, 3. But we wanted to think about the transformation that did in an easier way. We wanted to see if we could just turn it into a scaling transformation. We can, as long as we think about it with 1, 1 and 1, -1 as our basis vectors. And so we have to figure out how much of 1, 1 and how much of 1, -1 gets us 1, 3, or sorry, gets us 1, 3. Well, that's exactly what this multiplication does. Okay. Multiplying the inverse of this matrix will tell me how much of this vector and how much of this vector. So how much of this column, how much of this column do I need to get to 1, 3? Okay. And then once I have this new vector, it's the same point but in a different coordinate system. Now I can just scale because this tells me how many vectors. This tells me how many 1, 1 vectors I have, but when I in the transformation, when I multiply by the original matrix, 1, 1 just gets doubled every time. So I'm just going to double it 10 times. Boom. And 1 and -1, well, that just gets quadrupled every time. So I'm going to quadruple it 10 times. So I do this multiplication, and again, just 2, -1. 2, -1's the same as this, so I just dropped it down there and see how we're building this. And I can multiply all that together and I get this. But then this is an answer. It's just in eigenbase coordinates, and we'd like to have it in standard coordinates. So let's convert it back. And how do we convert it back? Well, this tells me this is how many 1, 1 vectors I have, and this tells me how many 1, -1 vectors I have. So this times 1, 1 plus this times 1, -1. Well, that's just another matrix multiplication. This times 1, 1 plus this times 1, -1. And so, and if I substitute this, so these are the same thing, right? If I substitute this in with this, and what do I have? I have these 3 matrices multiplied together times this, times our original vector that we're transforming, and I get this. So again, that's the same thing you'd get if you multiplied that, or multiplied this to the 10th power and then to times 1, 3, except this is a lot easier to calculate. Yes.
So basically what you did is you said the 3, -1, -1, 3 is equal to the B, and then B equals SA S inverse. And so then you just replaced the B with the SA S inverse and did it to the 10th power times the 1, 3.
That's right.
And then like this is kind of just explaining what that means.
Yes, this is, this tells, this is trying to understand a way of thinking about that, about why it makes sense with conceptually, is this converts from standard coordinates into eigenbase coordinates. In eigenbase coordinates, the transformation hopefully is just a scaling transformation, which is really easy, especially take powers of, and then this converts back to our standard coordinates. So whenever you see it, from now on, whenever you see that kind of like an S inverse, you can think about, oh, I'm changing coordinate systems. Or you can think, hey, does thinking about changing the coordinate systems help me? Okay, so this is right to your point here. Yeah, so we wrote this all out, but that means this to the 10th power times 1, 3 is the same as this times 1, 3. And if we're not worried about the 10th powers, we just get that this matrix is the same as this SAS inverse. And the power thing about it this way comes when you have to take powers. If you only wanted to find this times a simple matrix, you're not going to take the simple vector. You're not going to take time to do all that, right? At least usually you don't. And this is just to emphasize the point I already made. This, if you do the think about the multiplication, this times a vector, then this times that vector, then this times a vector, then this converts the vector to eigenbase coordinates. This scales it. in those in those directions, and then this converts back to your standard basis. Okay, and
Exactly.
there's some trouble in this room. You guys are just so awesome. They just blow for technology. That's fine. All right. So if B equals S inverse, if I have something like B to the 10th, then that's the same as S inverse to the 10th. And that's S inverse times S inverse times S inverse, S inverse, etc. So when you take off those parentheses, what do you end up with? Look at all these S inverse S's. All those products are just going to become the identity matrix. And then you have SAI, AI, oops, etc. AS. And that's just S A to the 10th, S inverse. So there's another way to see what happens with that S inverse form. You start taking powers, that S inverse S cancels out. So an algebraic way to see that. Okay, so any questions about the logic behind what's happening here, how we build that SAS inverse thing, how it's connected to eigenvalues and eigenvectors? Any questions about that? Okay. So mathematicians have generalized this. Not all matrices are diagonalizable, but it turns out if you can write them in this form, even if A and B aren't diagonal matrices, if you can find an invertible matrix P such that B equals P inverse AP, or the way we've been writing is this one, A equals PB P inverse. Doesn't matter which way you write it. Because if this is true, you multiply on the left by P inverse and the right by P, and those cancel out, and you end up with this. You can even write it this way. So if you multiply on the right by P on both of them, you end up with AP equals PB. Okay, different ways you can show that relationship. As long as there does exist that invertible matrix P where you can do this, then we say A is similar to B. Okay. We use the same sign as in for similar triangles or similar figures, that tilde sign. We say A is similar to B. There is a geometric interpretation. Can you talk about that? I might be able to mention it at the end. And you would have read about all of these properties that A and B have if they're similar. The determinants are the same. The same rank. They have the same characteristic polynomial. They have the same eigenvalues. A is invertible if and only if B is invertible. That's because if they have the same determinant, if A is invertible, then it's going to be non-zero. So B's will be non-zero. So we know that one's also invertible. Or they have the same eigenvalues. Well, then A is invertible if and only if 0 is not an eigenvalue. And so if A doesn't have 0 as an eigenvalue, B, and they have the same eigenvalue, B doesn't have that, and so B doesn't have 0 as an eigenvalue, so it's also invertible. And then we have these power rules. So A to the m is similar to B to the m for all integers. If they're invertible, you can actually do A to the -1 or A to the -2. So the reason these all hold, well, I should, any questions about these? The trace is also the same. We don't emphasize the trace as much as we do the determinant, but the trace is also the same. The determinant is the product of all the eigenvalues. So the determinant of a square matrix is the product of all the eigenvalues. The trace is the sum of all the eigenvalues. And so, so since they all have the same eigenvalues, you add those up, you're going to get the same. Okay, the reason these hold is because similar matrices actually do the exact same transformation, but they do it in a different basis. So if you rewrite your coordinates, if you change your coordinate system, you need a different matrix to do the same transformation, but those matrices are connected in this way. And so the reason that this all works out is if these do the same transformation but in a different basis, then multiplying by a vector by P inverse will change the basis. Will change, give the coordinates in a different basis, do that transformation, and then change it back to the original basis. So they do the same geometric transformation, but you just think about the two in different coordinates, so you need a different matrix to get the same transformation. I don't know if that makes any sense to you, but if it helps, great. If not, you can forget what I said in the last minute. You don't have to know that for the okay. So, all right, thank you very much.
It should be here on this side. And then you can
Yeah, quantum. Many worlds interpretation. Algorithm always ultimately surviving universally. There's one this. Yeah. You know what? If it works, it works. Yeah. Oh, algorithm. I appreciate that he universe has it.
Over with, right?
Is it really? Yes, just that term. We love Wikipedia. I swear, programming humor is literally.
Yeah, number 10. So yes.
Yeah, so I realized